Okay, so in the last part of the functions module, we will discuss interpretation of graphs. I've broken down the interpretation of graphs into 6 different parts. Right, there's very few ideas that I did not discuss, like the reflection about the x and the y-axis. Everything else that we discussed come from the components of the function. And so exactly as I said, the fact that we give these things names means that it has some significance. And where does it have the significance is when we are interpreting the graph. Okay, so yeah, so let's understand this stuff here and link it back to term 1 work, and you would see how the beauty of how everything starts to fit. Right, so let's look at this. When we talk about the reflection about the x-axis, then the y values become negative. So let me say that again. When you talk about the reflection about the x-axis, then the y values become negative. And so what I mean by that is the following. If you have this here, f of x is equal to x squared plus 2. If you want to reflect this graph about the x-axis, y must become negative. And so the new equation would be minus f of x. But f of x is what? F of x is the same as this here. So now because we have unlike terms, we have to parenthesize. So whenever you substitute, parenthesize. Therefore, the function that's reflected about the x-axis, or the f of x function reflected about the x-axis, will now take on this equation. If you want me to prove it, yet again, use the graphing calculator or sketch this function if you can. But let's use the graphing calculator just to ensure that we are as accurate as possible, okay? Right, so if we come to Desmos and we look at this graphing calculator, you can see the red function is the function f of x, and the green function is the reflected function, right? It's the function that is reflected about the x-axis. Now remember, as we spoke about reflections, we said that when we reflect a function, we need to do so perpendicular to the line of reflection and by an equal distance away from it. And so this is what we'll do, right? If I have to take this and put it into the whiteboard, this is what we get. If I bring the function in here now, you can see, if you look at this red function, see this point here has the coordinates 0 and 2, right? And it has 2 because of the y-intercept. Now, when you reflect it about the x-axis, what becomes the line of reflection? Remember, this is called the line of reflection. This line of reflection is the x-axis. And so when we reflect a point, we need to do so by the same number of distance away from the line of reflection. So this moved 2 units up, so away from it will be minus 2 units. Do that for this point. This is 1, 2, 3 blocks. This will be 1, 2, 3 blocks. There's it here. For this point, 1, 2, 3 blocks, 1, 2, 3 blocks. Can you see it there? See this point here. It's 1, 2, 3, 4, 5, 6 blocks. Do the same thing. 1, 2, 3, 4, 5, 6 blocks. There's it here. Same with this point here. 1, 2, 3, 4, 5, 6 blocks. 1, 2, 3, 4, 5, 6 blocks. There's it here. And if you do that for the infinitely many points that make up the function, then you would have the function that is reflected about or across the x-axis. Right, so that's what you need to remember. Right, when you reflect about the x-axis, y becomes negative. Okay, if we do a bit more a complicated example, you could get, let's say, f of x equals to 1 over x plus 3. Then how would this function look like reflected about the x-axis? It'll be minus f of x. Y becomes negative. So it'll be minus into 1 over x plus 3. Remember, f of x is the same as 1 over x plus 3. So wherever you see f of x, you input that. But because they have unlike terms, we have to parenthesize. So this will be minus 1 over x minus 3. Again, you take this and you plot this function and you plot that function and use the same logic of line of reflection. You would get the function reflected about the x-axis. Now, when we talk about reflection about the y-axis or reflection across the y-axis, then this is what we have, right? This is what we have. So let's say that we have the function f of x is equal to x squared plus 2. When you reflect something about the y-axis, let me say this again. When you reflect something about the y-axis, x becomes negative. So you need to write that down. X becomes negative. So f of minus x will be equal to, what this means is wherever I see x, I must put in minus x. So it'll be minus x squared plus 2. But see what happens. If I simplify this, I'm left with x squared plus 2. And so what we can see is that when we reflect the graph about the y-axis, x becomes negative, isn't it? But when we do that, we yield the same function before and after reflection. And so what we can conclude about the y-axis is that it is in fact the axis of symmetry. So remember, we are doing reflection But when you reflect something about a line of reflection and it yields the same function before and after reflection, then that line of reflection becomes an axis of symmetry. And so if I have to sketch this for you, you would see it in real time. Plus 2, and we had the function, let's put this here in brackets, minus x. See, minus x, and make this plus 2. Can you see that? The functions overlap. They overlap. They are the exact same function before and after reflection. So we can conclude that we actually have an axis of symmetry, which is the y-axis. And we've already come to that conclusion when we discussed the parabolic function. Now you can see it mathematically. Right now you can see it mathematically. Now I can do something a bit more complicated. I could say f of x is equal to x plus 2 squared plus 3. Right? When you reflect about the y-axis, x becomes negative, so it'll become f of minus x is equal to minus x plus 2 squared plus 3, right? Because wherever I see x, I input minus x. So basically what I'm saying is, we're supposed to actually parenthesize this, because where I see x, I put minus x. And so this will simplify down to minus x, be minus x plus 2 all squared plus 3. Now this is a function that we will do at grade 11. But if I show you the power of graphing, you would realize why I talk about the Desmos graphing calculator. Because you would see at grade 11, the axis of symmetry is not necessarily the y-axis. So let's sketch these two functions and you'll see exactly what I'm saying. So if I do this, I'll have x plus 2 squared plus 3, right? So x plus 2 all squared plus 3. So let's check this out. X plus 2 all squared plus 3, right? And then we'll have the same function, but we'll make x negative. I'd make x negative. See what happens. Can you see here now? Can you see here? Now it's more apparent that the function is reflected about the y-axis. So let's take a screenshot of this and explain it on the whiteboard. Right, if I explain this on the whiteboard, you can see here exactly what I'm saying. See the red function? Look at the red function. Right? Let's talk about this point here. We're reflecting about the y-axis. And when you reflect about the y-axis, this becomes the line of reflection. Remember, it's not yet an axis of symmetry, it's a line of reflection. So what you need to do is you need to reflect perpendicular to the line of reflection, and it needs to be by the same number of units. Can you see here? 1, 2, 1, 2. There's it here. Do the same thing here. This is 1 block away, so this must be 1 block away. There's it there. This here is 3 blocks away. This here must be 3 blocks away. This here is approximately half a block away. This is same, half a block away. Yeah, same thing here. Goes there. See, yeah, because this lies on the line, there's no movement to the left, so that's where both these points coincide. They both lie on top of each other, right? And if you do that for the infinitely many points, then you would get the purple function. This is why now you can't say at grade 11 that the y-axis is the axis of symmetry. Let me say that again. You cannot say at grade 11 that the y-axis is the axis of symmetry. It's not. Okay? So this is why you have to be very mindful when you're working with these things at grade 11. So you can see the y-axis won't be the axis of symmetry anymore. It just becomes a normal line of reflection, right? But there's the equations here. You can see the equations and how they change. Okay, and the equations prove it, right? Because we don't yield the same graph before and after reflection. Therefore, that cannot be the axis of symmetry. Let me say that again. You do not yield the same graph before and after reflection. Therefore, the y-axis cannot be the axis of symmetry. It's just a normal line of reflection. Okay, so now that we understand the reflection about the x-axis and the y-axis from a mathematical standpoint, let me tell you why this is so important when you look at it in terms of just the graph itself, right? You see, the reason this is important because I can sketch this purple function even if I don't have the equation for it. Think about that. If I knew that I want to reflect about this y-axis, then I just need to measure here, measure the same amount in the opposite direction but perpendicular to that line of reflection, and do that for the infinitely many points, and I can plot it. But this is where it becomes more useful. Watch here. You know, when we talk about the axis of symmetry for the parabola, we said that we basically yield the same function before and after reflection. And so why that is important, and more generally when we talk about the line of reflection, if I have the x-intercept to be 2 and 0 here, then I can tell you that the x-intercept here is minus 2 and 0. Just by using the property of the axis of symmetry. Because if I know the function is reflected about this axis of symmetry, so whatever I have on this side has to be the same on this side. It basically cuts the function in half. Then whatever I get here, if I move 2 units that way, I move 2 units this way, and I can locate every point on this side. And think about how powerful that would be, because if I have the roots, then we can do so many things with this function. We can do so many things, right? When we work with actual examples, you'll see how we can apply this in real time, right? And again, I told you that any time you reflect about a line, you call that the line of reflection. But it's only when you do the reflection and you yield the same graph before and after reflection, then only can you call that line a axis of symmetry. Okay, so that's very important there. Right, now we can move on to key points and features. So any question pertaining to symmetry or transformations, we're talking about these four concepts. Now we're going to talk about intercepts, intersections, turning points, maximum, minimums, and so on. So when we talk about the key points, the intercepts, let's talk about the intercepts, because I did give you a definition and I said I was going to elaborate on that idea. This is what I mean. Listen here. When you have a function that cuts the x-axis, so let me draw it like this here so you'll see what I'm saying, right? It cuts the x-axis. At the x-axis, y is equal to 0. And now let me make something known to you. There's only three types of values a number could be. It could either be negative, 0, or positive. Then you take these signs and you attach it to rational, irrational, and so on. But these are the primary three types that it could be, the signs of it. These are the three primary signs the number could take. And so what I'm saying is that at the x-intercept, y is equal to 0. If I move just a fraction to the left, what's happening to y? It becomes negative. If I move just a fraction to the right, what happens to the y value? It becomes positive. Where will this be important? You remember when we solved linear inequalities and we had this example here. Do you remember this? Do you know what this is? This here is in fact a line function. It's a linear function. And this is why I'm starting to link everything. Right? This is a linear function and I want to know, what's this? Where is y greater than 0? And so if I want to know where y is positive, exactly as I said, to do that we have to track the x-intercept. Why do we have to track the x-intercept? Because at the x-intercept, the function is, the y value is 0. If I move slightly to the right, it's positive, slightly to the left, it's negative. So that's why it will enable me to solve this question. And so if I have to sketch this function quickly, it will do something like this. And so what I'm saying is, at the x-intercept, y is 0. If I move slightly to the right, then I'm outputting all y values that are positive, isn't it, above the x-axis. And so the solution, even if I didn't solve this, I can tell you it will be x has to be greater than minus 1 over 2. So you can solve it from two perspectives. You can solve it using normal algebraic techniques, where you'll say 2x is greater than minus 1, and then x has to be greater than minus 1 over 2. But if you want to know why that is the case, you go and look at it from the standpoint of functions. Why is that the case? Because when I set the function equal to 0, because you know what we did here? We effectively found out the x-intercept. And so we want to know, okay, if I can locate the x-intercept, then I can locate the natures of the values. Because watch here, if I change this question and I made it less than 0, you see how this would change. Where would it be less than 0? It'll be all these values here to the left of minus half. So it'll be x less than minus 1 over 2. And so if you do this from a mathematical standpoint, you get the same answer. 2x less than minus 1, x less than minus 1 over 2. Right? For linear inequalities, not so important. Get to quadratic inequalities at grade 11. You'll see this happen repeatedly and why we need to have a visual. Right? We haven't even touched the most difficult questions yet. So if you can start adopting these ideas when we discuss easy questions, you will be a master at it. And so remember, for the x-intercept, we're talking about y values. What specifically about y values? We're talking about the nature of those y values. And what nature? We're talking about the negative, the positive, and 0. Because we know at the x-intercept, it is 0. But if I move slightly to the left, it could either be positive or negative. And slightly to the right, it could either be positive or negative. And so if we do this, check if we do this, and I draw the function like this. See, at the x-intercept, y is 0. Y is 0. If I move slightly to the left now, it becomes positive, and if I move slightly to the right, it becomes negative. Right here, you would know you would have a negative gradient. That's how you would sketch that function. We can apply the exact same idea with the y-intercept. For the y-intercept, if I have a function, there's the y-intercept here. If I move slightly to the left of the y-intercept, we have negative x values. If I move slightly to the right, we have positive x values. Right? But we very rarely tested on the y-intercept. Most of the time we talk about the x-intercept. But what I'm saying is, at the y-intercept, the x value is 0. Move slightly to the left, the nature changes. It becomes negative. Move slightly to the right, the nature changes. It becomes positive. Okay? Now you can take this exact same idea and apply it to what? The parabola. You can apply it to the parabola as well. Check here. Check here. See here. There's it here. Watch here. See, at these are the two x-intercepts. If I move slightly to the left of the intercept, y becomes positive. Here, if I move slightly to the right, y becomes positive. And in between here, in between this, listen to what I said, in between the x-intercepts, y is negative. But at the x-intercepts, y is 0. Can you see how at the x-intercepts, the nature of the y values change? So at it, it will be 0. Slightly to the left, it is positive. Slightly to the right, it is positive. In between, it is negative. I can do the exact same idea with the sad face. There's it here. Right? Yeah, if I move slightly to the left here now, it becomes negative. Slightly to the right here now, it becomes negative. At the x-intercepts, it is 0. In between, it is positive. So I can just move a fraction to the right and we'll have a positive y value. Right? Where would this be important? In a question, they'll tell you like this here. They'll say f of x is equal to x squared plus 2. Right. Then at the bottom, they'll say, okay, for what values of x is f of x greater than 0? What is f of x? F of x is the y values. And so what they're asking you, they're saying, okay, what x values must I input into this function such that I can output y values of the nature being positive? When we talk about that, when we talk about the nature of the y values, we have to think about the x-intercept. And so if I have to sketch this function quickly, it would do this. It would do this, isn't it? And so what we have here now is, we have no x-intercepts. And so the fact that we have no x-intercepts, we can say x element of real. And so what we're saying is, for any x value that I input into this function, we only output positive y values. It will never be 0. Right? And this, just to give you some foresight, this is what we call a positive definite graph. Because it will remain positive for all x values. Okay, so yeah, you can see in real time how we are applying all of these concepts and so on. Right, now let's discuss the next concept, which is turning points, right? Right, so now when we talk about the turning points lead to a very important discussion about maximum and minimum points, right? And it also leads to a very important discussion about increasing and decreasing functions. So these are terminology that we've already discussed, right? So I'm not going to elaborate too much on the definition, but I want to just basically supplement everything and show you how it fits when we're actually interpreting graphs. So at the turning point, remember the function either reaches a minimum like this, right? Or it reaches a maximum like this, right? So the way you would see it is like this here, right? Because it turns on the y-axis, or it'll look like this here, right? So it'll be a maximum. Now what's important to remember is that we got something called a global minimum and maximum, and we have a local minimum and maximum. And so, although you won't be tested on this, let me just give you some additional information. When we talk about a global maximum and global minimum, see this function here will have a global minimum and not a global maximum. Why? Because what the global minimum means is that this point here is the lowest point of the function. But it cannot be, there is no highest point because the highest point is infinity. So we cannot pinpoint a specific point that's the highest. Right? You're only allowed to have one global minimum and one global maximum. You can write that down, right? For this function here now, when we have a downward facing function, see this is a global maximum, but there's no global minimum, right? Because you can see that it goes all the way to minus infinity. So we can't pinpoint that exact area. When we talk about a local maximum and a local minimum, this is what you'll do at grade 12, a cubic function, right? So this is what a cubic function looks like. A local maximum is a maximum value within a specific range of x values, right? So within this range from here to here, the maximum value is this. But we know what the actual maximum is, actually infinity. So you can't say that this is the maximum because the actual maximum is here. You have to say that this is the local maximum, right? Right, and then when we talk about the minimum, we talk about a local minimum. So if we look at, let's say, this range of x values, this is the minimum value. But the actual minimum is here. We know it's minus infinity. This can't be the minimum because it goes to minus infinity. This has to be the smallest value, isn't it? And so this is why we call this a local minimum, right? Now, where this would actually apply in a realistic sense, and the reason why we bring this whole idea of local and maximum, when you apply this to real scenarios, you would see that exactly as I've explained repeatedly, is a function never exists for all values of x, isn't it? So sometimes you could have a function that looks like this here, right? And so we know that this here is the minimum, it's the local minimum, but the actual minimum is here. But if I have to make this a realistic function like time and sales or something like that, right? Then you know that this function won't even exist here, right? And this is why we come up with the whole idea of local minimum. Within this range here, this is the minimum value. So within a specific range of x values, this is the minimum. But if we expand the domain for all x values, then you know that this cannot be the minimum. This has to be the minimum, minus infinity. And so this is the reason why we say that we call this the local minimum or local maximum, because we have these scenarios where the function cannot exist for all x values. Right? There's no such thing as negative time values. And so this is why we bring the whole thing up of local. Right? The same idea would apply if we had a function that assumes this shape down. So this here is in fact a cubic function, right? If you got a curious mind, by now you would have put this on Desmos and you would have seen that cubic functions in general assume the shape here, right? And so if you're talking about cells and days or whatever the case is, then you would by now know that this part of the function cannot exist and this part cannot exist because we do not have negative sales values and we cannot have negative time. And so, and even though this function may take on the equation x cubed plus, let's say 2x plus 2x squared plus 3x plus, let's say 5 or something, right? Let's say it takes on the shape here. We're not talking about all the x values. We're only talking about a specific region. And so this is why we have a local maximum. So this here, what is the maximum sales of ice cream? There's it here, right? There's it here. So it starts in this region here. That becomes the maximum. But we know if you have to extend for all x values, the actual maximum is positive infinity, right? So this is how the local maximum and minimum actually comes up. Now we actually use it in scenarios, right? So that's about the turning point. What else do we need to remember about the turning point? Increasing and decreasing functions. So at the turning point, let me say this again. We call it the turning point. We call it the stationary point because at the turning point, the function is neither increasing or decreasing, right? And so if you move slightly to the left of the turning point, the function will either be increasing or decreasing. And so in this case, when you have a concave up parabola, the function will be decreasing, right? Because as x is increasing, what's happening? The function's y values are decreasing. At the turning point, the function is neither increasing or decreasing, and towards the right of the turning point, the function is increasing. And so when you are given a question about the function's behavior, whether it's increasing, decreasing, or constant, what do you need to first locate? You need to first locate the turning point. When you're given a question where they're asking you to check where the y values are either positive, negative, or 0, what do you need to focus on? X-intercept. If you're given a question where they're talking about where x values are positive, negative, or 0, what do you need to focus on? The y-intercept. So this is how you need to start training your mind to think, right? I could do the exact same thing with the downward facing parabola or the concave down parabola. At the turning point, the function is neither increasing or decreasing. Or for all values to the left, it is increasing. And then for all values to the right, it is decreasing. And so when you're given this questions, you'll know how to answer it. So if they ask you where the function is constant, it's the turning point. You find the turning point. If they ask you, and remember they'll ask you, okay, what is the x value? So then you put in x values. If they ask you what is the y value, you put in the y value. But more often we want to know what is that x value where the functions are increasing, decreasing, or is constant. Right? Then you're just going to locate the x coordinate of the point. Right? They'll tell you where is it strictly increasing. Strictly increasing will be every point excluding the turning point, isn't it? Because where is it strictly increasing? So it's here, exclude the turning point, and it'll go that way. So in this case, you'll say x greater than 0. Because for all x values greater than 0, it is increasing. If they ask you where is it decreasing, you'll say x less than 0. For all values less than 0, if I input any value into the function, it is decreasing. Right? I can start training your mind for higher order stuff. But for now, let's just leave it as this, right? Yeah. So that's what we talk about: maximum and minimum, global and local. When we talk about the measurements of line segments, we talked about this in analytical geometry. If you're talking about vertical lines will be y values. So it'll be y on the top minus y at the bottom will give you unit. It'll give you some units, right? That's how you measure vertical lines. For horizontal lines, it'll be x on the right minus x on the left. So how do you think about this? Now you basically think bigger x value minus smaller x value, bigger y value minus smaller y value, and bigger x values will always be on the right and bigger y values will always be on the top, right? So remember, this is relative. It'll be the higher y value minus the lower y value, the one that's towards the right minus the one that's towards the left. It's always relative. Yeah, so that's basically that. That's not difficult stuff there. And then we talk about the slope of a function. I've talked about this in depth. When we talk about the slope of a function, you analyze the gradient, right? And I told you that gradient talks about the rate of a function, right? But that's a calculus topic for grade 12. When we talk about increasing, decreasing, and constant, I've explained that. So what are we looking for more specifically is the turning point, because that's where it changes. Remember, I'm talking about negative, positive, zero. Same thing. Increasing, decreasing, neither increasing nor decreasing. Can only be three things. So that's how we thinking about it. Okay. The concavity of a function, to determine if a function is concave up or concave down. This is actually a higher order one, right? This is what we'll do at grade 12. But you can predict it from the value of a. Right? If a is greater than 0, you have a concave up function. If a is less than 0, you have a concave down function. Right? But this is actually used more at higher order stuff. When you talk about the asymptotes, it's a vertical or horizontal line that the function approaches but never touches. Then you read it from the equation. Right? You'll know that the q value for the hyperbola and the exponential function will give you the horizontal asymptote. The only thing you need to remember is that the vertical asymptote for the hyperbola is x equal to 0. So for the asymptotes, you need to remember the hyperbola always comes with 2 and the exponential function always comes with 1. Then we talk about something called end behavior. So we want to see how the function behaves as x approaches positive or negative infinity. If we draw this here as the hyperbola, if this x values continue to infinity, the hyperbola is going to become more closer and closer to 0. Right? So it won't become 0, but it'll get closer to it. So you get something like 0,00000000001. Right? If you want me to prove it, let's sketch it out. If I sketch this out here, and you would see, if I continuously go further and further away, right? If I go as far as I could possibly go, let me zoom out here. Can you see? This is how powerful this is. If I go for bigger values of x, and I put my cursor there, see what it's doing. 0,0000. Imagine if I go to 1,000,000, what it would become. Or you can even put it in your calculator. If you put this in your calculator, you put 1 over 1. And you just put 0,0000000. You just continuously add zeros because this basically shows x at positive infinity. Can you see that? You can't see that. It's 1 times 10 to the negative 33. So it's saying that it's going to more likely become 0, isn't it? And if you do that here on the negative side, if x goes to negative infinity, same thing happens. It'll go to closer to 0. It'll never become 0, but it'll get closer to 0. Right, then we can bring in the asymptote. Watch here. If I bring in the asymptote, let's say I call this here 1, y is equal to 1. And then if I draw the hyperbolas here now, if x goes to positive infinity, now the hyperbola won't want to become 0. Now it will want to become closer to 1. Can you see that? Even here to negative infinity, it would want to become closer to 1. Because now it doesn't approach the x-axis. We say more generally it approaches the asymptote. And so it would become more like the asymptote. But this is high order stuff, right? High order stuff. This, you rarely would ever get tested on this. Same thing here too. If I make this here y is equal to -1 and I draw an exponential function now, then what's going to happen if as x goes to positive infinity, this function is more likely to become -1, right? It's more likely, so the f of x, the y value is more likely to become -1. But it won't actually be -1. It'll be like minus 0,9999. Just a fraction before -1. Okay. Yeah, so that's that. That's what you need to remember there. And then again, I gave you this. I talked to you about this, discrete and continuous functions. You will not be tested on this, but you have information to actually contend with grade 12 stuff. So this is why I've taught this to you. But the discrete function just means that it exists at a point, and a continuous function basically means that it exists for all values of x. Right? There's no breaks or kinks in the curve. It's a continuous function, right? And then domain and range, I've talked about that extensively. Right? It's the interpretation type question. But when you talk about domain and range, you're talking about the set of x values and y values for which a function exists. And remember, I just said you just need to state the maximum and the minimum value for which the function exists, and if there are any restrictions in between. That's all you can think about. Maximum, minimum, and if there's any restrictions. That's all. That's what basically domain and range is. But what's important is that you need to learn how to state it in set builder notation and interval notation, because the examiner has the freedom to test it in any of these two notations that they wish. So you need to know, you have to be comfortable and flexible with the way you can denote them. Right, so that's everything that you need to know about graphs and interpretations. The only thing that we need to do now is work with some past paper questions and put all of this here to the test. Right, I can also teach you a lot of methods of thinking, like process of elimination and so on, but that can only be taught once we do questions. And if I teach it from a theoretical standpoint, it would not make sense. So we have to apply those ideas, right? So yeah.